Alright, here is the video guide part 2 for this lesson 10.1.3. Where I left off with this problem was I drew in my radiuses, being 5 and 5. I had my chord that was 6 units long. I put in a perpendicular bisector which cut that chord in half, so I have 3. I have still my radius 5. Now I have a 90-degree triangle in here, so I redrew that 90-degree triangle with the 3 across from the angle, the 5 being the hypotenuse, and my angle still missing, because I remember that what I'm doing in this problem is I'm looking for that central angle, because I know that central angle will be the same thing as the measure of arc AB, because central angle and arc measure are the same thing. And so what we need to do when we're looking at this right triangle is we need to figure out what theta is, and how we're going to do that is inverse trigonometry. Because if you remember, trigonometry will help you find side lengths, inverse trig helps you find angles. 3 is opposite of the angle, and 5 is a hypotenuse because it's across from your 90. So opposite, hypotenuse, and the fact that we're looking for an angle tells me this is an inverse sine problem. So we do sine inverse of your opposite, which is 3, divided by your hypotenuse, which is 5, and whatever that is, it gives us our angle or our theta value. If I plug this into my calculator, I go on there, I click the inverse button, so I get inverse sine. The inverse sine of 3 divided by 5 tells me that theta, or the angle, is equal to 36.87. Should have probably just rounded that to 9, that's okay. And then that's that angle right there. That's that half angle that we found, or that we were looking for. The issue is that we want the whole central angle, and so what we can do is we can take our angle here, multiply it by 2, and get the whole thing. And so what we'll do is we'll take 36.87, and we're going to multiply it by 2 to find our whole central angle. And so our central angle will equal 36.87 times 2 gives me 73.74 as my entire central angle. And we know, and I'll put that in red up here on my drawing, that entire central angle is this part right here. And we know that central angle always matches the arc that it creates. And so that arc that it's creating is that measure of AB. And so we actually have our answer here. The measure of AB is equal to 73.74 degrees. That's a really good problem, just because it involves so much of what we've been doing. Involved perpendicular bisectors from Tuesday, involved right triangle trigonometry from chapter 5, involved the idea of knowing your radius, knowing a chord, getting that chord cut in half by a perpendicular bisector, having the angle cut in half, and then at the end multiplying it by 2 to make it whole again. For time reasons, we'll move on to 10-27 here. If we have 2 chords intersecting, so this is kind of also was part of our, if you remember up here, we wanted to find the length of intersecting chords. That's what this is going to get into in this problem. Where it says to copy the diagram will be on your sheet as it is on mine, and I'm just going to use this here. So it says that chords AB and CD intersect at point E, and Timothy decided to create 2 triangles, BED and ACE. So I'm going to try to use a line here to create those triangles. BED would be a triangle looking like this, and ACE would be a triangle looking like this. Alright, so we have that part done now. So A is done, and because I added line segments BD and AC to make those triangles. Alright, the next thing it wants us to do is compare angle B and angle C, which is bigger. Well, actually, we talked about this very shortly yesterday, but angle B down here is an inscribed angle with its vertices being D and A. Its vertices being D and A. Angle C is an inscribed angle with its vertices being D and A. So when you have two inscribed angles and they share the same vertice, which means they create the same arc, those two angles must be congruent. And so we can say for part B here, part B, we get to say that angle B and angle C are congruent. Or angle B equals angle C because they're both inscribed angles that share the same vertexes. All right. How could I tell? I already said that. Likewise, compare D and A. Well, D, that angle, and A. D is an inscribed angle with B and C being its vertices, and A is an inscribed angle with B and C being its vertices. And so we also get to say that angle D and angle A are also equal, which is really big for us as we keep moving through this problem. So we'll go on to part C. That was actually a problem yesterday when we talked about inscribed angles and how if they have the same vertices or those inscribed angles make up the same arc, they are equal. I think that was in part 2 video of yesterday if you want to go back and take a look at that. How are triangles BED and ACE related? Nice question there. These two triangles, these two triangles are similar. They are similar. And they are similar because they have two angles that are the exact same, and that means that they have angle similarity. Look at all this lesson. This lesson's bringing back so much. It's awesome. And so there's our answer for part C. These triangles, they had D and A were the same, B and C were the same, so we have angle, and actually E is the same on both sides because that's a vertical angle, but we don't need that to say that they're similar. Now the last question is when we really get to put some work in here. We're going to use the idea of similarity here for part D. So it says if DE was 8 units and AE is 4 units, and so DE here is 8. AE is, I'm going to draw a line to it so I don't squish it in here. AE is 4, and EB here is 6. We're looking for EC. We don't know what it is, so I'm going to put a question mark. All right, these two triangles are similar, and it's kind of hard to tell which sides correspond. And really the way I see it is that if you wanted these triangles to correspond, you'd have to have this angle A land on top of angle D because those are the ones that are the same, and you'd have to have angle C land on top of angle B. So really if you can kind of picture this triangle ACE flipping onto EDB so that these angles lined up, you could see that the corresponding sides are DE and AE. And so what we're going to use is we're going to divide those corresponding sides to find a zoom factor. And so what I'm going to do is I'm going to take AE, this is going to be for part D, I'm going to take AE and I'm going to divide it by DE to find my zoom factor from small to big, or sorry, from big to small. AE was 4, DE is 8, which gives me 1/2 is my zoom factor. And so if I want to go from big to small, I need to multiply by 1/2, just like 8 times 1/2 gives you 4. So 6 times 1/2 is going to give us our question mark, our missing part. And so 6 times 1/2 gives us our missing side. I could call that question mark EC. 6 times 1/2 is 3. So 3 equals the question mark, or I do want to change that question mark to calling it EC. I believe EC, right? Yes. Equals EC. So some interesting things about intersecting chords. We see that in this case, and I believe in many cases, we would create similar triangles because intersecting chords will have these arc lengths being shared, which means that their inscribed angles will be the same. All right, last one we'll move on to, one that I think is really interesting. I have 5 minutes to finish it up. We'll see how long it takes to do. A polygon is said to be inscribed in a circle. If you think back, we talked about what inscribed means, or what a polygon inscribed in a circle means. Looks like this. In a circle when each of its vertices touch the circle. How are the angles of a quadrilateral inscribed in a circle related? Consider this as you answer the question below. So what we have is, for ABCD inscribed in a circle, we're going to try to solve for x. All right. What we have here is, and I'll try to put it the best I can, your inscribed angle here is always half of what your central angle is using the same vertices. So my inscribed angle goes to vertices B and D. So I'm going to try to do a central angle here that is marked at B and D. And I'm going to put one there and one down here. All right. It looks kind of funny because that's 100 degrees, and actually the central angle now is over 100 degrees, is over 180 degrees, which makes it this kind of obtuse, crooked line here. And so if that's 100 degrees and that's the central angle is 2 times bigger, and so the central angle there is 200 degrees. Which means the measure of BAD, the measure of that major arc BAD, is going to be 200 degrees. And I'm going to write that one down. So the measure of the arc BAD, of bad, and that's a major arc because it's majority of the circle. That measure is 200 degrees. So I'll put that in red. This major arc here is 200 degrees. All right. Well, if that's 200 degrees, then the question really we can ask is, well, then what's the remaining part of the circle? And if that's 200 degrees, then what we can do is, well, there's 360 degrees in the whole circle. We can subtract away the 200, and we'll be left with 160 degrees for that blue portion of the circle. All right. Well, we'll see what I can erase here. I might even delete these lines. All right. So what we have was BAD was 200, BCD was 160, and so what that means is, if I can draw my central angle again, this central angle here for BCD, that central angle in there is 160 degrees. It's the same as the measure of the outside. And remember that if the central angle is 160 degrees, the inscribed angle that goes along with it, because vertices also at B and D, is always half of that. And so x actually gets to be, we can say what it is already, which is cool. X is going to be the 160 degrees divided by 2, which gives me 80 degrees. And that's my answer, 80 degrees. Again, if you've noticed, this lesson's really a lot about knowing that measure of the arc, and then that's the same as the central angle, and then the inscribed angle is half of that. That's been a really big part of this lesson. All right, let's see if I can finish this up. Alejandra noticed that I think that the opposite angles of a quadrilateral inscribed in a circle are always supplementary. Is she correct? The answer is yes, she is correct. And the idea goes with what I was just saying. We know that, we know that, I'm going to try to move this out of the way quick. We know that that central angle, the two central angles that make up this entire circle, the two central angles have to add up to 360. All right, which means the two inscribed angles are always cut in half of 360, which means those two inscribed angles have to add up to 180. And if they have to add up to 180, that means that they are supplementary. That's not a very formal proof, but that's my quick proof, so I don't have to go to another video. Make sure you take a look at the math notes and email me any questions about inscribed angles or central angles or anything.